Hello and welcome back for lecture 11. This week we'll be talking about performance. So in the previous lecture we talked about a few different things. We forged ahead with our simple redux. In that one we did an asynchronous action. We then saw that it might not be good to change our implementation of Redux in order to do that. And so we found out what Redux middleware was. And by using Redux middleware, we were able to add asynchronous actions to Redux itself. Then we talked about another Redux add-on called Redux Persist, which allows us to store our state into whatever storage mechanism we want, and then rehydrate our app based on that information. We then talked about what the difference was between container and presentational components. So if you remember, container components are the ones that are hooked up to your Redux state, and then they pass down props to what are considered presentational components. And so presentational components are they only care about the props that they need to display themselves. We then talked about a couple different tools that we can use for writing JavaScript, those being ESLint, which allows us to enforce some style rules, and Prettier, which allows us to automatically rewrite our files such that they abide by these rules. So this week we'll be talking about performance. And so what exactly is performance? Performance is how quickly or how efficiently something works. And if we want to make that better, we can do what's called performance optimization. And by doing that, we can make something work as efficiently as possible. Performance optimization is actually a very, very wide field, but today we'll only be talking about optimizing the JavaScript side of things. We'll mostly be talking about high-level things with a few examples along the way. So one thing that's important about performance is knowing that there are actually trade-offs involved. So by optimizing performance, we usually pay some sort of cost, and this cost is usually in your application's complexity. So in most cases, it's actually not worth optimizing your code. JavaScript now is so fast that by optimizing, you add complexity to your app, and sometimes that complexity and maintainability is really not worth the little to no gains that you'll get from optimizing. And so in general, you don't want to over-optimize anything until you found a bottleneck. And by bottleneck, I mean something that's slow enough that that one particular thing slows down your entire app. And so how do we actually measure for these things called bottlenecks? Well, there's a few things actually built in. First, we need to remember what environment are we running our application in. And so there are actually two different environments built into Node or our bundler. One is production, and one is non-production, or what most people consider development mode. And so the way that we actually set this is in the XDE. If you click this gear icon here, there's a drop-down where you can change host, and you can also toggle this thing called development mode. And so by checking this and unchecking it, I can actually determine whether or not my application is running in development or production mode. Important to note, if I change this, I should actually restart the bundler such that it actually is indeed running in the mode that I want it to be. React actually has a few optimizations that it does when it's in production mode. And so things like prop types aren't necessarily checked, and warnings and errors are not necessarily displayed. So there's a few tools built into React Native itself that allow us to benchmark our performance. And so one is called the React Native Perf Monitor, or Performance Monitor. What this does is it shows you the refresh rate of both your UI and your JavaScript thread. So if you remember back to our lecture on React Native, we talked about how there was one thread for rendering the UI on the native side, and one thread that's actually executing your JavaScript. And so this React Native Perf Monitor allows us to see the refresh rate on both these threads. And so anything below 60 frames per second means we're actually dropping some frames. And so there is potentially a bottleneck in whatever we're dealing with. And so to show you how that works, I'm running this simple application here. What we can do is shake the device, and it brings up this menu. And we can click the Show Perf Monitor. And that shows this thing here, which is draggable, which shows us a few things. One is how much RAM we're actually using. So how much memory is your application consuming? And of that memory, how much is being consumed by the JavaScript itself, or the JavaScript core? We then see how many views are in our application. The top number refers to how many are currently in view, and the bottom number is how many there are just total. And then we see the two things that I mentioned, the UI and JavaScript frames per second meters. And so since they're both locked at 60 frames per second, it means we're not dropping any frames, or there's no bottleneck in what we're currently doing here. And so what happens if we actually want to introduce a bottleneck? And so if you remember back a few lectures, we implemented this application where we just display a bunch of contacts, and these contacts are generated by that contacts.js file that we talked about a few weeks ago. And in this case, I actually reverted back to our scroll view. If you remember scroll view versus flat list or section list, the flat list and section lists are virtualized lists, which means they only render what's currently in view, whereas the scroll view will actually render everything before displaying. And so if we toggle it and then turn it back on, we see that our JavaScript thread does indeed drop well below 60 frames per second. So once again, we can toggle this, and then when we toggle it again, it has to render all of these contacts. I believe there are 1,000 being shown, and we see a dip in the frames per second in our JavaScript thread. Cool, and so by using this perf monitor, we can navigate through our app and find out exactly what screens are causing any frames dropped. If we want more detail, we can use what is called the Chrome Performance Profiler. And so I alluded to this a little bit last week, where we can actually run our JavaScript inside of Google Chrome. And so we've done this a few times in the past. And what this does is it shows you a flame chart of all of your components. And I'll show you what that means in just a second. But one thing to note is that this is only available in development mode. If you're running your application in production mode, this option will not be available for you. And so since we are indeed in development mode, we can use this debugger. And so what I did was shake my device, bring up this remote debugger. I clicked on it, and it's now running my JavaScript inside of Google Chrome. And so we talked about how the JavaScript is actually separate from the UI threads, and the way that they communicate is through this bridge. And so it doesn't really matter where our JavaScript is running, as long as it can communicate with our UI thread. And so since it's running currently in Google Chrome, I can inspect and see what's going on. And so here you can see elements, console sources network. But the tab we're actually looking for right now is performance. And so here we see a bunch of options. We see we can click the record button or press Command E to start a new recording. We can click the reload button, which will reload the frame and record the page load. Unfortunately, this doesn't really work in React Native. It's more something that's geared towards web. But what we can do is we can press the record button, do a few things in our application, and then come back and see exactly what has happened in our JavaScript. And so let's toggle these so that they're not visible. Let's start a new profile recording, go back, toggle them. You see that it took a while to render, and then we can go ahead and stop this profile. And then Chrome will analyze things and show us this chart here. And so we see frames, interaction, main, raster, GPU, user timing. And what we're looking for here is user timing. If we dive into user timing, we can see a few things. We see the React tree reconciliation. We see contact screen update, which is our contact screen that we have here. We have a view, scroll view contact, scroll view mount, and then we see a bunch of things. And if we zoom in all the way, we can actually see that each one here is a row being mounted. And so this is what a flame chart looks like. A flame chart is a chart that is basically our React tree, but graphed out over time. And so we can see these numbers up here, which correspond to the timeline since we clicked that record button. And what is happening as these milliseconds tick by? So you see 3,600 milliseconds, 3,650 milliseconds. And so in this 50 millisecond time span, what has happened? Well, we have been rendering our scroll view contacts. We've been rendering our scroll view. And within that millisecond thing, we see that all of this happened. And what exactly is there? Well, we can zoom in and see that we've rendered a few rows. And what happens at each row mount? Well, there's a view in there, there's some text, there's another text, and there's a text context. So we can see that for every single component that we have in our tree, each one takes a little bit of time to render. And we can see exactly what's being rendered by looking at this flame chart. And so if we refer back to our code, we can see that the app, all it's doing, I removed a lot of the stuff that we did last week since it's not necessary for this particular example. I have my ESLint thing popped up. We can see that this app is only doing one thing. It's rendering provider, which, as we remember from last week, is what allows us to access the store, our Redux store, anywhere in our app that's given to us by React Redux. We see a view, which just has a few different styles. And we have our contacts list screen. And so what is being rendered there? The contacts list screen is just rendering our contacts list. And what exactly is our contacts list? Well, it's defined here to be the scroll view contacts. And what is scroll view contacts? We can see that it's just, let me silence these errors real quick. So I'm running pretty really quick just to silence those errors. And then now I can view without my ESLint integration popping up. And so scroll view contacts is just a scroll view. And what it's doing is it's taking our contacts, which is an array that's passed down. It's mapping over them. And for each contact, we're rendering a row. And so we can actually see this exact structure of our app in that flame chart. And so we saw our app. We saw that it's rendering something called the contacts list screen. We saw that the contacts list screen is actually rendering the scroll view contacts. And we see that the scroll view contacts is a scroll view with a number of rows that corresponds to the number of contacts. And if we, again, refer to that flame chart, we see our app, which is the top level component. We see our contacts list screen. We then see that it has a view inside of it, and inside that view, we have our component called the scroll view contacts. We see that that is actually rendering a scroll view, and so if we just double check the code, we can see that we have indeed a component called scroll view contacts, which is indeed rendering something that is a scroll view. And then inside of that scroll view, we see a large number of rows, and each row is referring to a row that is rendered right here. And so this is just timing for us all of the components that we have in our tree. And so it might be inefficient to render all 1,000 rows when we want to just mount that app. And so what we want to do instead, well, we saw a few weeks ago that we can actually, rather than using a scroll view, we can use a virtualized list, a list that only renders what's in view currently. So let's go ahead and do that. We have implemented from a few weeks ago that section list contacts. And in here, we are actually using a section list, which is indeed a virtualized list. So again, let me silence these errors. So here, disable this next line. And here as well. So this should shut up those errors. And so we see here that we have our section list, which does a little bit of logic in order to separate our array of contacts into the data structure that the section list is looking for. And then it goes ahead and renders a section list. And so this is code that we wrote a few lectures ago. And we see that we pass it a render item, which it will use to render the items as they appear on screen. And so it's important to note that only what's currently in view is being rendered. It's not rendering all 1,000 of these contacts before it's showing it on the screen. And so let's go ahead and in our contacts list screen, we can go ahead and flip this Boolean here so that it's rendering the flat list contacts rather than the scroll view contacts. I just did this so it's easy to do this quickly during lecture so I don't have to type. So we can now see that this now renders almost instantaneously. It's just because it's only rendering what's in view. And so let's now do this again. Make sure it's not in view. Start recording a profile. Render the view. And then stop. And now we can go ahead and see this flame chart to see if it's rendering as many contacts as the scroll view did. And now we see something very different. We see over here our app inside it a virtualized list. It turns out the virtualized list within it has a scroll view. And let's see how many rows are being rendered. So we see, now we get to peek into the internals of how this section list is being rendered. So we see that there's a view with a cell render. Inside that cell render is the row being called, and inside that is a view. So inside the row is exactly what we have inside our row implementation. It's a view with a couple pieces of text in it. Those texts are just the name and the phone number. But we see that 1, 2, 3, 4, 5, 6, a lot fewer than 1,000 of these are being rendered. And the reason is because it's only rendering what's in view. And so we can actually see proof of that by, one, just toggling the button and seeing that it renders almost instantaneously, but two, actually just looking at this flame chart and seeing that within this scroll view here, there's actually only like 15, maybe 20 rows that are being rendered, rather than all 1,000 like the previous one. And if we wanted to take a peek at the internals and see how this works, we can see that this virtualized list, or our section list that we're using, is actually calling a virtualized list under the hood. And that virtualized list is actually using a scroll view under the hood. And so we get a peek at the internals of this component. And so let's now stop remote debugging so we can forge ahead. So now that we've seen how to actually look at the performance of our app, let's start to actually optimize some things. So what are some common inefficiencies in apps, React Native apps? So one is just re-rendering way too often. Another one is unnecessarily changing props. And lastly, unnecessary logic in mount update. And so what does it mean to re-render too often? Well, components actually automatically re-render whenever they receive new props. We've been talking about this since nearly day one. But sometimes a prop that isn't necessarily needed is passed. And then if that changed, it also requires the entire component to re-render. And sometimes that's completely unnecessary. And so how do we actually go about fixing that? Well, if we're using something like Redux, we only need to subscribe to the part of the state that we actually care about. And so in our map state to props function, no need to subscribe to some props that aren't necessary for the app. So that one's a pretty easy optimization. Another thing is using keys in arrays or lists. And so in a few lectures ago, we talked about why that's necessary. And so if you remember back to then, the way that React works is that every single time a component is re-rendered, it will actually diff something in the virtual React tree with what's actually rendered to the app. And so if we have something like a list of maybe names, and maybe the first one is Jordan, and the second one's David, and say we wanted to add a new person. If we wanted to add somebody like Yoan, and we wanted to add it to the third place in the list, it's pretty easy for React to do. It says, OK, we need to add something to our virtual list and say this is what's currently on screen, or this is what's currently on screen. And this is what it's doing in memory. So it can say, OK, we're going to add Yawan to the list here. And so let's do this in red. And then it can go ahead and do a diff, which is what's actually there. It says, oh, this remains the same. Don't need to change it. This remains the same. Don't need to change it. Oh, Yawan doesn't exist in the actual tree, so let's add him here. Easy. All we had to do is add one person at the bottom. But what happens when we don't want to add the person to the bottom? So let's retrace our steps a little bit. Say the goal was actually to add Yawan to the top of the list. Then what needs to happen? Well, if React was just to do its thing in diff, it would say, OK, let's add Yawan here. And now we have this new list. So what's different between the first people in the list? Well, they're different, so let's change this. How about the second person in the list? Well, Jordan is different than David, so we need to change that. And then who's third? Well, nobody's there, so let's just, oops. This should be Jordan. And then nobody's in the third list here, so let's just add David. So what ends up happening in this case is we changed all three things when we really only needed to change one. And so by adding keys to a list, React can actually keep track of what was in the new list that was originally in the list, even if the order has changed. And so if we, let's just redraw this. If in our old list we had Jordan and David here, and then we want to add Yawan to the beginning, what happens in this case if we were to mark them and say, maybe Jordan's ID is just the number 1, and maybe David's ID is the number 2, and maybe Yawan's ID is the number 3? And so now we've marked them with what are effectively IDs. So what happens now? React says, oh, we need to add Yawan to the beginning of the list. And now let's diff what is in the new list, in the memory, with what we actually have here. Oh, Yawan 3 doesn't match Jordan, but this here actually has a number 1, and we see that the number 1 is here. Oh, we also see that David is still here. So we don't actually have to change these. We know that what used to be part of the items that used to be in the list are still in the new list. They just changed their orders. So we can actually just move those components down the list and add one new person here. So React is smart enough to know, hey, these particular people didn't change. They just shifted places in the list. And so in the new list, now that we don't have to recreate them, we can just shuffle them around, reuse them, and add only what's needed to be added. And the only way that we can allow React to have that optimization is by marking people with these IDs. And these IDs must actually be unique. Otherwise, it won't know, say we had some third person here in the list with an ID of number 1. When it sees Jordan 1 here, it won't know which one it should be. And so it'll actually throw a warning, oh, key error, we have multiple of the same keys. And so the constraint on this is that we must have unique keys. But by assigning keys to each member in a list, React can have this optimization. And lastly, we have should component update, which we talked about in the previous weeks when we talked about React lifecycle methods. Should component update is a lifecycle method that allows us to either return true or return false. If we return true, we're answering the question, should the component update, with yes, and it will go ahead and re-render. If we return false, then we're answering the question, should the component update, with no, and it will actually not re-render. And then we see this new thing called a React Pure component, which we have never talked about so far. So we've talked about a React.component many times. What is a React.component? Well, it's just the basic building block of React. And what does it give us? It gives us things like state. It gives us those lifecycle methods. But it turns out there's another thing called a React Pure component. And what differs here is that a pure component has a predefined should component update, where it just does a shallow diff of props, meaning it looks at the props that it used to have, it looks at the props, the new props that are coming down, and will compare each one. And it does this at a shallow level. And I think we talked about a shallow merge back in lecture 1, but it just means it will look at each prop. It will say, does this prop triple equal this new prop? And so if it's something like an object, it won't actually dive into the keys of the objects. It'll just see if the object references match. And same with something like a function or an array or any other object type in JavaScript. So let's go ahead and do something here. So let's add something to our app that will actually change the first contact in our list. So let's revert back to our scroll view, just so that any performance hits are noticeable, because it is re-rendering 1,000 rows at once. So now you can see that it takes a good second in order to render this full screen. And so let's add something like some sort of button maybe here, where when you click this button, it just changes the first person in the app. And presumably, we won't need to re-render all 999 other people, but we'll see how we can tell React explicitly, hey, don't re-render these. And we're going to use something like should component update. So let's just do a quick review of what's actually happening here. So we have our contact screen. We can toggle the contacts, which is just something in state that decides whether or not we should render this list. This list is just a scroll view, which maps over all the contacts that we pass it and renders a row here. And what is a row? Well, a row is just a very basic view with a couple text things within it. And so let's first implement this change. And so we're going to need some way to tell our app, hey, we're going to do something here. And generally, when we're talking about a Redux app, when we want to tell our app to do something, and by do something I mean change something in our state, we want to do that by dispatching an action. So let's first add an action for what we want to do. So within our actions.js, which is where we define all of our action types and our action creators, let's add a new action type for changing the first user. So we just added the action type, and now we are going to add an action creator, which is just a function that returns an action. And if we remember back to a couple lectures ago, an action is just an object with a type and maybe payload key. So let's export something called change first contact. It doesn't take any arguments, and it just returns an object with a type that is change first user. Let me change this to contact. Cool, so we now have our action type. And so when we dispatch this type, we need some sort of thing that is listening and will change our data. And so we do that in the reducer. And if you remember our reducer right now is just built up of two smaller reducers. One handles the user part of the app, and one handles our contacts. And so since we're changing the contacts, we should update our contact reducer, which is up at the top here. We have a contact reducer is passed some state, which is initialized to our contacts in an action. And if our action type is update contact, we add a contact. And now we're going to add something that says if our action type is change first contact, then we should do something else. And let me remember to import that from our actions. And so what do we want to do here? We want to change our first contact and do that in a way that is immutable. Because if you remember back to the lecture on Redux, every time we change our state, we want to do that immutably. And so we need to figure out a way to extract the first contact in our contacts list, change it somehow, and then add it back in. So how might we do that? Well, let's use some shorthand here. So just like there's shorthand to pull keys out of objects. So say we have, we want to get the action type, we could do something like this. Which is basically declaring a new const called type and assigning it to the type key of the action object. We can also do some pattern matching on arrays. So we could do const first contact, and the rest of the contact is equal to that array called state. So in other words, if state were something like name, Jordan, phone, some phone, and there are no other people in this array, what would happen is first contact would match to Jordan, to this object here, and the rest is just an empty array. And so we'd be left with first contact is this object up here, and rest would be an empty array. And so this allows us to destructure an array and assign it to a couple values. And so now that we have the first contact out, what we can do is the new contact is going to be an object, because we're doing this immutably. We're creating a new object here. We can take the name, or let's actually take all of the key value pairs of first contact and just clone them. So if you remember what this ... notation is doing is saying take all of the key value pairs in an array, in an object called first contact, and put them into this new object that we've just created here. And so this effectively immutably makes a copy of first contact. And now let's overwrite the name and say the name is just going to be my name. So now we've immutably updated new contact so that it's a clone of the first contact, but we're overriding the property called name and replacing it with my name. And now let's return some new state. And what is the new state? Well, the first contact is actually going to be the new contact here. And then the rest are just going to be whatever was there before. And so a quick recap of what's going on here is the state comes down as whatever the state used to be. We're matching on the type change first contact. And then we're using this shorthand in order to grab the first contact in our list. We're just assigning the rest into this variable that we're just to hold them for now. And then we're modifying new contact. And we're doing that immutably. And so we're creating a new object by using this object literal notation. We're copying over all of the key value pairs of the first contact. And then we're going to overwrite one of those. And so we're overriding the name, and we're changing it to my name. And then lastly, we are returning a new contact with the rest. And then we can make this a little bit safer. So say there are actually no contacts. Maybe if there's no first contact, just return the state. So that just makes it a little bit safer in case there's nobody in the first contact. Cool, so now we've added an action which notifies our reducer that we want to change our first contact. We've added that logic in the reducer to actually change the first contact. And now we need to effectively fire that action off. And so how are we going to do that? Well, let's go into our screen and open our contacts list screen. And so let's add a button here which fires that off. And so let's import that action. We called it change first contact from our Redux actions. Let's create a new button that says change first contact. And then all we have to do on press is just change first contact. Right? So now we go here and we click change first contact, but nothing happens. So what is going wrong here? So let's just sanity check. So we import change first contact from our Redux actions. So let's go see what that does. So change first action, change first contact here is a function that takes no arguments. And so when we click the button, it's invoking this function with no arguments. So that's all good. And then it returns an object that has a type key that is equal to change first contact. And so what is our bug here? Why is nothing happening when I'm clicking change first contact? Well, all that's actually happening is we're invoking a function that returns an object. But nowhere is that letting our Redux store know that it should be dispatching an action. And so how do we bind that function, that action creator, to our dispatch function? The answer to that question is by using React Redux. And so if we go open up our contact list screen, we see that we've already imported that connect higher order component from React Redux. We're already using it down here by mapping our state to our props. And now we just need to say, also bind our action creators to our dispatch. And which one do we want to bind? Well, it's the one called change first contact. And so that is now binding our action creator called change first contact to a prop that is passed down called change first contact, which is a function. And so here, rather than invoking the action that we imported from our actions file, which is really just a function that returns an object, we want to invoke this .props.change first contact, because that's the one that's actually bound to our dispatch function. And so if we save that and click this, we see that it did change the first contact. And we can do it again, and it has changed the contact again, but it doesn't really matter because we're changing the name from Jordan Hayashi to Jordan Hayashi. And we see that it takes a little bit of time. So let's refresh our app real quick. It takes a little bit of time to actually do that because it's changing this and then re-rendering our entire list. We can make that even more obvious if we up the number of contacts that are being displayed. So let's just open up the contacts file, change 1,000 here to 5,000. And now it's rendering as we speak. And now it's taking quite a long time. And if we click this, we see it takes multiple seconds before it renders. And why is that happening? Well, when we click change first contact, what happens? It goes off to our Redux store and updates the first contact, and then passes it back down here. And what happens? It renders that first contact with the new name. And then it renders the second contact with the exact same information, and renders the third contact with the exact same information that hadn't changed from the last time. And so it's actually going down and re-rendering 5,000 people where really only one of them changed. We're extraneously re-rendering 4,999 contacts. And so let's try to optimize that. So we know that we can use this thing called should component update or React peer component, and it basically just says, hey, if our props don't change, don't re-render me. And so how are we going to do that? Well, we want to do it in the row, because row's the thing that's ultimately receiving the props. And right now, row is just a stateless functional component. It takes some props and returns an element. So let's actually make it stateful. And so by making it stateful, it can remember its old props and react accordingly. So let's actually do class row extends react.peer component. And so by using a peer component here, it's the same thing as a component with one thing changed. The should component update lifecycle method is already implemented for us, and it just does a shallow diff of the props. And so let's do that. Let's have a render method that returned this. And so all we changed is we wrote, let's silence ESLint. We wrote a what used to be a peer functional component, and we changed it to a class component that extends React peer component. And if you actually looked at the lint errors, there's an error here where props is not actually defined, because in a stateless component, what is props? It's actually this.props. And so we can actually create a variable called props, which is equal to this.props. So I can just do that rather than adding this in front of those other ones. And we can actually use the shorthand here and do const props equals this. Or in other words, this we expect to be an object. We expect it to have a key called props. And so let's create a new constant called props and assign it to the value of the key props. And so now, if we save this, now each one of the rows is a peer component. And again, it's taking a few seconds to render. But now for each row here, these are peer components. And so they're React components that have a should component update lifecycle method defined. And what it's doing is it says, all right, when you pass me new props, let me see what my current props are and check to see if the new props are any different. And if they're not, I'm not going to re-render. And if they are, I will. And so now let's click that change first contact button and see what happens. It was pretty instant. Again, let's refresh. It's going to take 5 or so seconds to render the entire list. And we see that when we click this button, this changes in much less than 5 seconds. And what's happening here? Well, it's seeing, well, one, it's dispatching that action off to a Redux store. It's changing the first contact. It's then passing those props back down to this component. And then it's re-rendering this component. And for each row, it's passing down those contacts. And for the first one, it sees, hey, my name's different, so let me re-render. And then the next one, it says, all right, is my name the same as it used to be? Yeah, it is. Is my phone number the same as it used to be? Yes, it is. So now I don't need to re-render at all. Now I only need to just pass. And so it does have to do 5,000 equality checks for each, one for each row. But the simple equality check there is much faster than re-rendering the component. But what if we're passing props that we don't intend to pass? We're passing maybe much more than name and phone. And so we can actually optimize this further by saying, we know that the only thing that might change is the name, really, in this case. So we can actually optimize this further. So rather than doing a peer component, let's just do a normal component. And let's define our own should component update. And should component update is past the next props. And we can check. Well, we know, since I wrote the code, I know that the only thing that could possibly change is the name. So I can just check if the next props.name is different than the current props.name. I can return true. else I can return false. Or in other words, just return the value of this Boolean expression here. So instead of saying if this is true, return true, otherwise return false, I can just say return next props dot name is not equal to this props dot name. So if we now run this, it again takes 5 or so seconds in order to render the first time. But now when we want to change the first contact, that's actually roughly twice as fast as the previous one, because instead of doing 5,000 checks, where each check is checking every single prop, it's only checking a single prop. It's only checking name. And so by defining a should component update, we save our component from re-rendering too often. So what's next in our common inefficiencies? Well, unnecessarily changing props. And so what might actually happen here is we accidentally, or maybe not accidentally, unknowingly, change a value that is passed to a child and cause a re-render of the entire subtree. And so if you remember, the way that a React app is expressed is it's just a tree of a bunch of nodes. So we have our app, and then maybe our app has a couple different components. And maybe this one has a few different components. And maybe each of these has a few, and so on. And so every single time we pass down new props, the entire subtree is updated, or could be updated, depending on how it's implemented. And say these two things are pure components. Pure component. Pure component. So now what happens? If we pass down props that haven't changed, then the re-rendering is stopped there. So again, if app updates its state, but the things that these two nodes rely on, those props don't change. Since they're pure components, they say, OK, I'm good. I don't need to update. But say we accidentally change one of those apps, change one of those props, and we pass a new prop down to this. Then the pure component says, oh, I was updated, or one of my props at least changed. So now let me re-render everything below me. And so if we accidentally pass a prop that shouldn't have changed but actually changes, then we are at the risk of re-rendering an entire subtree when we don't necessarily need to. And so this is something that we see all the time. So say we have an object or an array or a function or anything that can be expressed as a literal. Say we have an object literal in our render method. That means every single time this component is rendered, a new object is created, just because it's an object literal in that sense. So this means we might be rendering something that we don't intend to. And so let's take a look at an example that has this side effect. So let's implement something called a pure button. And we'll only use this for an example. All it is it's going to be a button that will change colors if its props are changed. So let's just import React from React. Let's import button from React Native. And let's export default a class called pure button, which extends React.pureComponent, which, as we learned in the previous slide, is just a component that will check to see if its props have been updated. And if so, it will re-render, and if not, it actually won't. And let's just render and return a button where it just retains all of its props. And let's actually do something additional. So let's have our state default to a color of null. And if the component updates, so component did update, let's set state and update that color to be something red. And let's also pass that color down here. So in other words, we have a button. Oh, and excuse this ESLint error. So we have a component here, what we're calling appear button. And all it does is it has a state which initializes as a null color. And so when it renders, it's just going to be a button. It's going to pass all of its props just straight through to a button. But it's also going to say, hey, I have a special color that at first is just null. It doesn't have a color. But if I ever update, I'm going to change myself to be red. And so this component here is just going to show us that it'll turn red if we accidentally update it. So let's now create a new screen. Let's have a screen that, let's just copy it from our contact list screen. So this screen is not going to have much. We can actually delete these things. It's probably going to be faster just to rewrite it. So let's have a screen. First, we need to import React. We're going to import a view from React Native. And let's render this view. And since I'll be quick, I'm just going to put the style inline. And what should we have happen when we click the appear button? So let's first say the appear button is going to have some style that will align itself to be centered. And on press, what should we do? Let's have it count. So we're going to need a count here. So this class extends React component. It's going to be initialized with a state that starts at 0. So if you recognize this example, it's the example that we gave on almost the first day of class when we were discussing React Native. Let's have a render method which returns this. And what's going to happen on press, let's do this.setState and do the previous state, and then return the count plus 1. And then close that view. And in theory, this should, every time we click the button, it should increment the count. And maybe we should actually show the count. So let's also import some text. And display it. And let's also remember to import our appear button. And that should close those errors. So cool, we just implemented the app that we had on nearly day 1. And let's go ahead and render it. So import that appear button screen. from peer button screen and render it. So now we have, we forgot to give a title to our button, so let's go ahead and do that. And now we have our thing. So we can increment the count if we click it, and it will increment that number in the top left. We click it, and uh-oh, our button turns red. But it's a pure component, so it shouldn't be re-updating. And so remember, if we have any object literals in our render method, it's creating those object literals every single time render is clicked, or render happens. And so since in our render here, we have a peer button, every single time this render is created, this object is getting recreated. And so if we remember back to day one, we were talking about things like a style sheet. And so we can go ahead and use a style sheet here, which will guarantee that it won't create a new object every single time we re-render. And so let's do const styles equals a style sheet.create, something you should be pretty familiar with at this point. And let's have our button style be align self-center. And then go ahead and use it down here. Great. So now it's not going to create a new style object every single time we render. And so now we can see that we click it, and uh-oh, it still turns red. So even though we changed our object that was getting recreated every time, we still have here a function literal. And since we have just a literal function definition here, it's actually recreating that function every single render method as well. And so every single time we render this peer button, we're passing down a new function. Even though it does the exact same thing, it's actually a completely new function reference. And so what we can do here is declare a class property. So you can say increment, and all it does is this.setState, and takes the previous state and sets the count equal to the previous state's count, and add 1. And so now down here, rather than declaring a new function, we can actually just use this.increment. And it's complaining, but now it'll run if we click. Oh, goody, it's not turning red. But that's strange because we still have a string that we're just declaring here. So why isn't peer component re-rendering even though we're declaring a new string literal here? So if you remember all the way back to one of the first lectures, we talked about the JavaScript primitive types. We talked about how there were numbers. There were many other types, including strings. And lastly, there were objects. And anything that wasn't one of those primitives was an object. And every object gets recreated when you so sorry, the way that you compare these things when you compare them with triple equals, objects, their references will be changed. And so if we declare a new object and we want to compare it by doing a triple equals, if it's a new object, no matter what's inside of it, they're going to be different. Whereas for the primitives, when you compare them with triple equals, you're just seeing if their values are the same. And so even though this is technically a new string that we've gone ahead and created, when you compare those, since it's the same exact string, the peer component will know, oh, it's the same one, I don't need to re-render here. And so let's please this ESLint. And now this does behave how we actually wanted it to. And why is that? Well, it's because the title isn't changing. The styles we're not declaring in line. We actually brought it out to a separate style object here. And same thing with this function. And you see it's no longer turning red. And so the last common error, so the way that we fix this is by using constants or methods or properties on the class instance, which we just saw. So let's look at the last very common error that I see, which is unnecessary logic in a mount or an update. So this one is a lot more subtle than the others. But adding class properties to an instance, so adding properties to that particular instance of a class, instead of methods on the class. And why is this bad? Well, properties are created at every single mount, whereas methods are created just once ever. And so in other words, when we create something like this, which is a class property, which is set equal to a function, as I explained when we first talked about this syntax, it's basically the same as doing a constructor here. Invoking the super, and then doing this dot increment equals a function that does this. So that means every single time this app is, or this component is constructed, it creates a new function and sets it equal to this. Whereas if we had instead done something like this, this is a method, and this method is only created once at the time of creating this module. And so something like array.map isn't created every single time we create a new array. It's just something that lives on the array prototype. And so it's only created once. Whereas here, same thing. If we implement increment as a method here, it's only created once at the time of this module's creation, rather than every single time this component gets mounted or created, which is effectively what happens when we do this as a class property as such. And so this is one of the things that might get you, because if you had actually done it as a class method like this, what happens? There's actually a bug here, and we've seen this bug many times. We'll click, and we say, oh, this .setState is not a function. Why is it not a function? Because what is this when increment gets invoked? It's not this class. Who knows what it is? And so there's actually a bug here, and so we actually do need to bind this to the instance. And so this is actually a time where it might not be worth implementing this small optimization. In fact, you can't even do it in this case. But there are cases where if you have something like render, where every time render is invoked is always going to be in the correct this context. That way, we don't have to implement render as a class property. So it's possible that we wanted to bind render to this class, and we can do that by using this notation. But since every time render is invoked, it's using the right this context, we don't have to. And so that is a small optimization. But again, remember, there are trade-offs for all these optimizations. And what is it? Well, these performance optimizations come at complexity costs. And oftentimes, it's just not worth the cost and complexity and maintainability. So don't forget, don't over-optimize until a bottleneck is found. So let's go ahead and take a quick break. And then after the break, we're going to look at a specific optimization built into React Native. Hello, and welcome back. So before the break, we were talking about performance and a few of the common pitfalls in React. And we ended with me reminding you that a lot of these pitfalls are less performant, but it's not necessarily a bad thing. Oftentimes, optimization comes at a cost that is too great. The complexity that you end up adding to your app is not worth the marginal benefits that you get in terms of cost. So let's talk about a time where it often actually does matter to be as performant as possible, and that's in animations. And so if you remember back to project 1, we implemented what was a Pomodoro timer. And so let's add a progress bar to that timer. So this progress bar should show us how much time is left in the timer. And so the animation that we're about to create is going to require both the JavaScript and UI thread. And so let's go ahead and do it. So I have it running here. So this is just a solution. It has a work timer. It'll switch to a break timer. 25 minutes is probably too long for us to sit here and wait to see the progress bar go up. So let's actually modify the code. So the code is conveniently copied into the repo if you cloned it before class. So let's actually first just take a quick look at exactly what this is doing. So for those of you who took a look at the solution that I released a few weeks ago, this is basically the exact same solution cut and pasted. But let's just take a look at what it's doing. And so in app, we declare a couple things. We declare the defaults for work minutes and break minutes. So let's actually adjust those to be something like 0.1 minutes. Or 6 seconds each. And so if we save that, we'll see that it got reset to 6 seconds each. But here we have a couple things. We have our state, which has a work time and break time, where the work time and break time are measured in seconds. We then have something called time remaining, which is the same thing but measured in milliseconds. We have a flag that is letting us know if the timer is running or if it's paused. And we have a flag that lets us know if the active timers work or break. When the component mounts, we create a new timer. I created a timer class, set the state to be running. And then every single time the timer ticks, we pass this function called update time remaining, which is declared here, which just sets the state. It does a bunch of other stuff, but let's go take a look at what the timer is, how it's implemented. So let's look at the utils. I created a timer class to encapsulate all of the logic for timing. And so this timer takes a duration, how long the timer should be in milliseconds. It takes what should it do every time it ticks, a function, a callback there. And what should it do when it hits 0? And so it goes ahead and saves all of those values. It then goes ahead and creates what should be the end time, and it starts ticking. And what happens at every single tick? Well, if the time is less than, if the end time is less than what it is now, then it means we're done. So let's invoke the callback with 0. Let's invoke that onEnd function. Otherwise, it means we're still ticking. So let's invoke the tick function with however much time we have remaining. Let's figure out exactly what time it should be when we want to tick next. And so by moduloing the time remaining by 1,000, we get however many milliseconds there are left until the next second, or until the next tick should be. Then we create a timeout to invoke the same exact tick function again, that amount of milliseconds later. And so this accounts for any delays if the JavaScript thread was full, or if there's some time drift or something like that. And this makes sure that the next tick should be as close to the second as possible. And then we have some logic for handling stop, but that's a little bit less relevant for right now. And so let's go ahead, go back into our app, and let's try to create a progress bar right here that will just grow and grow to the full width by the time our timer gets to 0. And so how are we going to do that? Should we implement that in our app component? Probably not. It sounds like it should be something that's encapsulated into its own component. So let's go ahead and do that. So let's create a progress bar. And it's just going to first import React from React, import probably a view, and maybe also a style sheet from React Native. And that's for now, just export empty view. And let's import it into app. All right, so we have our progress bar, which all it does is just render an empty view. And let's import it into and use it into our app. So we have our countdown, and let's just put it directly below the countdown. We want the progress bar here. Cool. So nothing should have visually changed. It's just an empty view. We can style it so that we are sure that it's actually appearing. So maybe let's do so let's have the progress bar just be a height of 10 and a width of 100. And let's make it blue. So now we should see a blue bar appear, which is not actually happening because I need to actually use that style. So now we see a blue bar appear. And so we're going to want to have that bar increase in width as our timer goes down. And so what information are you going to need in order to ensure that that happens? So what information do we have? We have the time here, which is the time remaining left. That's probably going to be important information because the bar is going to be of different width depending on how much time is left. We probably also want to know how much time there is total. And so just having 1 second left doesn't really give us enough information that we need to know how wide it should be. So it needs to be 1 second left out of how many? Out of the 6 seconds that were total for the work time. So we need to know both the time left and the time total. What else do we need to know? Probably nothing else. So let's go ahead and pass those props down to our progress bar so that we can go ahead and use them. So here, what do we have at our disposal? We have work time and break time. So we need to figure out exactly which one of those to use. And we have time remaining. So that's already there. So we can pass the time remaining into our progress bar. Remaining. And we want to have the total time. Let's call it time total. So we need to figure out how to calculate that. So let's just write a helper method here. We can do get total, get time total. And what is it going to do? Well, let's get the work and break time. So const work time is this dot state dot work time is, I believe, what I called it. Yep. And const break time is this dot state dot break time. So there's probably a better way to do this. So the shorthand here is const work time and break time is this dot state, which is the shorthand for these two lines. So we can just replace that. And then we can return if this dot state dot, I think it's called active timer. Yep. If this dot state dot active timer is work, return work time, otherwise return break time. So this helper method is just a simple function that gets the work time and break time and returns the correct one depending on what the active timer is. And so that will get our total time. So let's do this. Let's do this dot get time total, and that will get the correct amount of time. There's a potential bug here because that time is measured in seconds and this time is measured in milliseconds. So let's get ahead of that by multiplying this by 1,000. Cool. So now get time total is in the same unit of time or measurement as the time remaining. Now they're both in milliseconds. And maybe it might be helpful for this to know if it's running. Cool. So now let's go ahead and open up progress bar. Let's actually use prop types here just so that we can remember exactly what props we have. So what did we pass? We passed something called time total, or time remaining, which is a number. We passed time total, which is also a number. And we also passed is running, which is a Boolean. Cool. So now we have a progress bar. We're passing down the props that we want, which is just the time remaining, time total, and is running. And right now it's just showing a blue bar. But there is a bug here where at line 13, I forgot an equals. Thank you, Yuan. And now, yeah, it's just a blue bar. So how are we going to get that bar to show the correct width? Probably some math. So let's do some math. So in React Native, there's actually a really easy way to get the width of the window. We can import dimensions from React Native, and we can do some calculation here. So before we return, let's figure out exactly how wide the window is. So const width of the window is dimensions dot get the window width. So this will get us the dimensions, which is both height and width. So we can just do dot width, because that's the one that we want. Or again, we can use that shorthand where we destructure and grab the width out of that object. So now we have the total width of the window. And if we wanted to, we can actually just pass that in directly. So we have the width here. Oh, I typed widow. I now see why you're laughing. We don't want the widow's width, which is kind of a funny statement. We actually want the window width, and so we do indeed get the correct width of the window there. So now let's go ahead and do some math. So we know exactly how much time is remaining. We know how much time there is total. And so we could figure out using some proportions exactly how much of that width of the window we should take. So let's do const percentage is just the time remaining over the time total. And I'm grabbing those from props. Cool. So now I have the width, and I have the percentage of the width I want to actually take up. And we can just do here the percent times the width. And so hopefully we should now have a timer where the width is proportional to the time left. unfortunately is going in the wrong direction. The way I had imagined it was just a progress bar that grows from the left to the right. So again, not that hard to do with math. So the width, that's the inverse of the width that we want. So we actually want the width minus that. Or we could do the inverse of the percent. So 1 minus that is the percentage of time that has been occurred. And now we can see it grow from the left to the right, just like I had imagined in my mind. Unfortunately, the way that I imagined it in my mind was also a little bit smoother than it is currently. Right now, it's only happening once per tick. So as the seconds count down, a big block of the progress is achieved. So how might we optimize this? How might we actually make it do what we want it to do? Well, there's a few ways. Maybe we should just make it tick more often. And so we saw the code for the timer. We see that the way that this calculates when the next tick should be is it just modulos by 1,000, meaning it's going to tick again at the next 1,000, the next second. So we can make this number smaller and have it tick more often. So let's declare a constant up here called tick duration and set it to a second at first. So we can just replace this with the tick duration. And now it'll do the same thing, 1 per second. We can say now the tick duration is going to be a half second. And we'll see that it now does twice per second. Let's make it go even faster. Maybe 1/20th of a second. Now it's going pretty dang smooth. Let's actually just make it run at 60 FPS. So let's just do, this would be 1 frame a second, and let's actually just divide it by 60. So now we have 60 FPS. And dang, is that smooth. So cool, we got it, done, easy. But there's not really much happening in this app. It's just a timer that ticks. But what if this app was actually doing other stuff? What if it was busy? What if the JavaScript thread once in a while would actually get full? So let's actually write a function that will randomly block the JavaScript thread, because why not? It'll simulate a lot of work being done. So let's go back into app. Let's write a block statement. You might recall this block statement when I demonstrated it in maybe lecture 1, was it? But all we're going to do is say const done time is the current date. And let's make it block for 200 milliseconds. Not that long, 1/5 of a second. And so let's do while the date.now is less than the done time. Don't do anything, just loop. And in the render, let's say if randomly so flip a coin. If it's heads, block. And so now we'll see it's getting really jittery. And why is that? Well, this thing is ticking once every almost close to 17 milliseconds. And each render, there's a 50% chance that it's going to block randomly for 200 milliseconds. And so now we're seeing the progress bar get really janky. It goes smoothly, and then the JavaScript thread gets busy. It blocks for 200 milliseconds, and then goes again. And so we see what people refer to as jank. And so how might we fix this? Well, the current animation that we wrote requires both the JavaScript and the UI thread to run. And what's happening? Well, it's sending messages over the bridge tens of times per second. It's actually not cheap to do that. Every single time we do that, we need to serialize any of the information that needs to get sent to the other thread and back and forth. That's happening 60 times per second. It's quite a lot. And blocking either thread will impact the user experience. And as we see here, this is blocking the JavaScript thread, even though it's ultimately should be running on the UI thread, and it's causing some jank. It's really actually hurting our user experience. So how can we go about fixing this? Well, this is React Native, right? We have the React side and we have the native side. So let's just implement the animation in native. Easy peasy. We all know Swift, right? We all know Objective-C. We all know Java. I don't. So this requires knowing many other languages, which a lot of people don't. And so this probably isn't the correct way to do things. But what if we could declare the animation in JavaScript, we all know JavaScript, and have it run on the native thread? That would be pretty cool. And it turns out that's already possible. And so there's this API called animated. This allows us to declare a computation in JavaScript and actually compute it on the native thread. So now the JavaScript thread no longer needs to compute anything. So if this was an expensive computation, it frees up the JavaScript thread to not have to do it. And in addition, the JavaScript thread can be blocked, and the animation will still run. It'll even run smoothly. Though there actually is a small caveat to using this, that we can't use this native driver for layout props. But the API documentation is here if you want to take a look. I'll allow you to go read the documentation, but I'll do a quick demo on exactly what this looks like. So currently, again, real quick, what's happening is we're declaring this computation. This computation is actually just doing a quick percentage. It says how much time is there left, how much time was there to begin with. We know how approximately the percentage, we know exactly the percentage of what the progress bar should be. We compute that in JavaScript. We say, OK, the width should be this amount. We know it should be this percentage of the way done. So we can multiply those two. And lo and behold, after all this math, we have the width that we want. Then we send that width over to the native. It'll re-render that view so that the view's width is that width. And good. It's good to go, except for the fact that our JavaScript thread is randomly blocking. So now let's implement this such that it runs completely on the native thread. So let's just copy the progress bar to progress bar animated and import the correct thing. So now it's using the animated one. It's still janky because we didn't actually change anything. So now let's go ahead and use that new cool API. So what is the first thing we need to do? Well, we should probably import animated. So now we have this really powerful animated API. And so this gives us a few different things. It gives us this thing called animated.timing. And what that is it's a function which will, you can say, use this value as the reference. And so the native thread is going to compute everything, and it'll store it in this particular value. And as this value changes, again, all of this computation is being done on the native thread. But as it changes, just tell me what you want me to do, and tell me how I should change it. And so the way that we do that is we actually use this animated.timing function. So in order to do that, we can no longer use a stateless functional component here. So let's make this a class. So now it's a class. It does the exact same thing, except prop should really be this.props. So quick, easy way to fix that. Again, it's doing the exact same thing. It's a component now, but that didn't really help us at all. So how can we actually make this better? So let's store in our state now this percentage. This is going to be a new animated dot value. And this just started at 0. So this is basically saying I'm going to store in my local state, so only I need to know about this. I'm going to store a value that starts at 0. Eventually, it's going to get to another value. Maybe the value is 100, maybe it's 1,000,000, maybe it's anything I want. But for now, it's going to start at 0, and I'm just declaring it as a new animated value because it's subject to change. It's going to be changed at a pretty high frequency, and it's going to be computed all in the native thread. And so when this component mounts, I'm going to create a new animation. I'm going to do this dot animation is animated dot timing. And it takes a couple things. We first want to tell it what value we want it to animate. So it's going to be this dot state dot percent. And it's going to take a configuration object. And what does it want? Well, it's going to want a value that it should eventually get to. So it's starting at 0. And it's eventually going to get to maybe 100. Since we did percentage before, we can do percentage now. So we're going to give it a 2 value. We can give it 100. It's also going to take a duration. So how long should it be until it gets there? Let's just do the duration is going to be however much time is remaining. So this dot props dot time remaining. And it's also going to take some sort of easing function. Or in other words, how quickly should this number go up and down? So we could give it maybe a cubic if we wanted it to start slow and then get really fast. Or we could give it sine, or we can give it a quadratic, exponential. But really, we just want it to be linear. So every millisecond that goes by is so if a millisecond goes by at the beginning and a millisecond goes by in the middle, it's going to increase at by the same amount. And so the easing function we want to give it is going to be the linear function. And so we're going to have to import easing from React Native, which is built in and linked from the docs. So now we have an animation. It's not really doing anything. We're starting it at 0. The animation, we store a reference to the animation. It goes up to 100. It's going to take as long as the time remaining, and it's going to do it in a linear fashion. But we should probably start it. So bam. So now we have an animation. It starts at 0. It'll eventually get up to 100. It's going to take the time remaining to get there. And it's all going to happen on the native thread. So that number is going to scale from 0 to 100 at 60 FPS, presumably. And it's going to update that state and all compute on the native thread. So now what do we have to change here? Well, unfortunately, there's a caveat of this native driver. It can't affect layout props. And so we can't actually change width. We can't change the flex property. We can't change height. We can do is we can actually scale the x dimension of our app. So one thing I'm actually missing is it's not actually running on the native side. So there's a prop that we need to pass called useNativeDriver. True, which basically says, hey, we can compute it on the JavaScript side, but actually use the native side for this, actually compute these things on the native side. So cool, now this is presumably going to update that state value very quickly. Now we can do down here, rather than scaling the width, let's actually transform it. So let's do transformation. Transform takes an array. And the first one that we want to do is this transform or scale x, I believe it's called. Let me check my notes real quick. It is called translate x. I believe it's actually called scale x. I'm not going to trust myself before, and it's going to scale by this percent. And this percent, we're no longer computing it here. It's actually going to be computed in the state. Computed on the native side and stored in this.state.percent value. So now let's do transform is const percent is this.state. We no longer use props. And let's do percent times width. So again, same thing. Let's see if this works. It's not going to. And it's saying, oh, syntax error, unexpected token on line 38. Because this needs to be an object. It's not going to work because I'm not going to wait for it to bundle, but it's because this is just a normal view, and normal views can't actually get connected to these animations that are being computed on the native thread. We actually need to use a special thing called an animated view, which is just a view, but it can watch these values that are being animated. So let's go ahead and do this. It crashed. And as it reopens, I realize there's another bug here. It's the width needs to start out at some number so it can be scaled. And I wonder if that was causing the crash, because you can't really scale a non-existent width. Nope. All right, debugging time. So style takes styles.progress. It also takes a transform, which maybe I should trust myself and call this transform. Translate x. Oh, this needs to take a. Okay, so I had the API incorrect in my mind. It's scale x, and it doesn't just take a number. It takes a number, an input range. Okay, so what's really special about these animated values is that it can interpolate itself and graph itself out on a line. And so as the number grows, we can also tell it to map to a particular value. And so percent right here is not a number. So you can't just multiply percent by a number. So what used to be percent.width times width doesn't work. Why is that? Because percent is not a normal number. Percent is an animated value. And so you can't multiply an animated value by a number. It's just going to crash your app, as we saw, and which made me panic a second ago. What we need to do is we need to interpolate that animated value into a number. And you do that by doing that value dot interpolate. And so by interpolating this value, we can say, OK, this value is going to be a range from some number to some number, and that should map onto some target range of some number to some number. And it'll do the math automatically to get those proportions. And so we know that the input range starts at 0, and it goes to 100. How do I know that? Well, we declared that it starts at 0 here, and we declared that it's eventually going to get to 100. And what do we want to map it onto? Well, the output range should start at 0. And what do we want it to get to? We eventually want it to get to the width of the application. So now, hopefully, this won't crash our app, because we're no longer incorrectly multiplying an animated value by a number. We're instead taking that animated value and mapping it onto some value that starts at 0, ends at 100. So that's the range of our animated value. and we're mapping that onto some value that starts at 0 and ends at width. And so we saw that it started at 0 and ends at exactly halfway through. And so the way that the scale is calculated is that we need to start at 0 and get to 2 times the width, or you can just make this 2. And so now it scales correctly from 0 to the left all the way to 100. And even though our app is still getting blocked by the JavaScript thread as often as it was before, so we never remove that code in app.js, that will randomly block. It's still blocking half the time, and half the time every tick. So very often it's going to block randomly for 200 milliseconds. But we see a completely smooth animation. So it goes, there's no jank at all as it goes left to right. And if we replace this with the non-animated progress bar, we'll see that there is indeed jank as the JavaScript thread gets blocked. So that's awesome. We were able to, with somewhat few bugs, go ahead and create this animated progress bar that does all of the calculation on the native thread. And so we see that even though the JavaScript thread is blocking, this still works perfectly fine. Unfortunately, it's not doing everything we want to. When the break timer gets reset, the bar is just still full. So let's go ahead and fix that. So let's do component will receive props. And if we're resetting the timer, so in other words, if the next props dot time remaining is greater than the current props dot time remaining, which will only happen when we're resetting the timer, then what do we want to do? Well, let's do this dot set state. The percent is going to be a new animated value that starts at 0. And then after that happens, so we need to make sure it resets the state, we're going to restart this animation. So let's change component did mount to be called start animation. And when it mounts, let's go ahead and invoke this dot start animation. And then if we reset the timer, let's go ahead and reset the animated value. And after that's done resetting, then go ahead and pass a callback that will start the animation. Because as we talked about in the prior lecture, you can actually pass a callback to set state, which will invoke after the state is set. So now we see that as the timer goes down, even though the JavaScript thread is randomly blocked, it's very smooth. And when the timer gets reset, the animation gets reset, and everything is good. Unfortunately, we're out of time, and so we won't go ahead and implement the pausing, but hopefully that has given you enough of a taste of the animated API to go explore it on your own. So great, thank you for joining us today, and tomorrow for our final lecture, we'll talk about deploying apps and maybe a little bit of testing. Thank you.